Hi everybody, welcome to another video in Trigonometry, section 5.3, double angle and half angle identities. Right, so this is the continuation from the previous section. Let's just review what we have. If we have sine upper sum, for sine, we will have a product of different functions, so sine and cosine, and then of course cosine and sine. The sign in the middle though is the same, because if we have a difference, then we will have a difference. So that is sine. Now for cosine, the product of the same function but the sign in the middle is opposite. If we have a difference, then we're going to have the sum. Right, so that's what we have. Like I said on the previous section, most of all the identities in this section we derive from these two. If we want to prove these two identities, it will be difficult. But knowing this, the rest will not be as difficult. Of course, the tangent is a sum right, and if we have a difference, then we will change the sign. Right, so now we're going to use this identity to prove this. We have sine of 2a is equal to 2 sine and cosine. We can use u or a or b, it doesn't matter what the angle is, but we're going to prove that. So the first one, I write that as the lower Roman numeral, lowercase Roman numeral. Right, sine of 2u is 2 times sine of u cosine of u. Right, this will be straightforward. I start from the left hand side, sine of 2u. Now sine of 2u we can write them as u plus u, which gives us 2u, right? And then we use the sign of a sum, be sine u cosine u plus cosine u sine u. These two terms are the same. Combine like terms give us 2 sine u cosine u, and that is the right hand side. So straightforward, right? Next, cosine of 2u. Now the cosine, we have a lot other option. Cosine of 2u can be written as this, or as this. So we can write cosine of 2u equal to one of those three. Right, we're going to prove that. So first we do the same thing. Start from the left hand side, and then 2u is u plus u. Now And then we can write as cosine of cosine minus sine. The angles, all of them are u. Now, cosine times cosine is cosine square. Once again, I don't emphasize this enough. When we write cosine square like this, we mean cosine times cosine, or cosine times cosine. And none of this equal to that. Is completely different things. So now cosine times cosine is cosine square minus sine square. Of course, that is equal to the first one, so which is good. Yeah. Now how do we prove it equal to this? And as mentioned before, quite often than not, every time when we have cosine square and sine square, we will use the Pythagorean identities. So sine square plus cosine square is equal to 1. So if we want to solve for cosine square, it equal to 1 minus sine square. And if we want to solve for sine, it is equal to, if we want to solve for sine square, we subtract the cosine square to the other side. And if we solve for cosine square, we subtract the sine square to the other side. Right. Now we just substitute back into here. Now we end up with this one, right? So the left hand side is equal to cosine square minus sine square. Now if we substitute sine square using 1 minus cosine square, and that gives us cosine square minus 1 plus cosine square, and that gives us 2 cosine square minus 1. Of course, that is equal to this one. Now, same thing, if we start from the left hand side, we will have cosine square minus sine square. But this time, we write the cosine square using this. And minus sine square make that 2. So that's what we have equal to this. So it's pretty straightforward. As mentioned before, those 3 identities we derive from most of the identity we have at the end of this chapter. Right. Number 3, we're going to prove the tangent. Tangent of 2u is equal to 2 tangent of u over 1 minus tangent square. Right. This also straightforward. We start from the left hand side, and tangent of 2u is tangent of u plus u, and tangent of a sum is going to be that tangent of u plus tangent of u over 1 minus tangent of u, tangent of u. That gives us 2 tangent of u on the top, and the bottom is 1 minus tangent square. And that equal to the right hand side. So pretty straightforward. As long as we know these identities, the double angles identities will be very straightforward. Right, now let's look at some example. If we have cosine is equal to negative 3 over 5, theta is in quadrant 2, find exact values of sine of 2 theta and cosine of 2 theta. Right, let's just write first sine of 2 theta equal to, according to the double angle identity, it's going to be 2 sine and cosine. Right. We know the cosine, which is given negative 3/5. We don't know the sine though, so we have to solve for the sine first. So that's we don't know. This one's okay. Right, so let's go back over here and then try to solve for sine of theta. Right, so we have cosine equal to that and theta in quadrant 2. Now cosine is x over r and equal to negative 3 over 5. Of course r is always positive, so x can be negative. So from here we have x equal to negative 3 and r equal to 5. Straightforward, right? Cosine is x over r. And then the Pythagorean theorem, x squared plus y squared equal to r squared. And we will solve for y squared. Of course we did this many times. And y squared equal to 5 squared minus negative 3 squared, or 5 squared minus 3 squared. 25 minus 9 is 16. And take the square root on both sides. So y equal to plus or minus, don't forget the plus or minus square root of 16, or plus or minus 4. Right. Next, it is in a quadrant 2. If a point in quadrant 2, the y values is positive. Yeah, so that is because it is in quadrant 2, so y values is positive. It is still above the x-axis. Right, so we have y. And finally, if we want sine, it's y over r, and y is 4 over r 5. So that's what we have. Sine is 4/5, and we substitute in here 2 4/5, and cosine negative 3/5. And that gives us 2, 3, 4, negative 24 over 25. Right, so it's really straightforward. Next, we find cosine of 2 theta. Now, cosine of 2 theta, there are a few more options. There are 3 options exactly. Cosine square minus sine square, 2 cosine square minus 1, and 1 minus 2 sine square. So those are one of the 3 options that we can choose. And of course, we can choose any of them because we both have sine and cosine. However, it would be better if we use what is given. So we use the one that only have cosine, namely 2 cosine square minus 1. So 2 cosine square is negative 3/5, and we have negative 3/5 square minus 1. So 2 times negative 3 square the top, give us negative 3 square, and let's just write like this, and minus 1. So we have 2 times 9/25 minus 1. So give us 18/25 minus 1. And that is of course negative 7/25. The common denominator is 25. So 18/25 minus 1. Change the fraction. Negative 7/25. Right. One thing we can check though, here we have sine and cosine. Sine square plus cosine square is 1, right? So we have negative 24/25 square plus negative 7/25 square. Sine square plus cosine square is 1. So that is correct. So it's a nice thing that we can check. Right, so pretty straightforward. Now let's verify this is called the triple angle identities. We don't need to memorize this, but we can derive whenever we need. So sine of 3x. So let's start with that. Usually when we prove identity, we start with the more complicated sign and go to simplify it. However, sine of 3x, we don't know that what it is equal to, so we might want to start with that. So left hand side is sine of 3x. And similar to, by the way, usually when we write the sine of 3x like this, we mean sine of 3x. And we rarely have, this case, sine of 3 times x. So usually when we write sine of 3x, it is equal to this and not that. Yeah. And even put the square here, that means this. Okay, that's different story though. Right, so sine of 3x meaning we have sine of 3x in the parentheses. 3x, we can say x plus 2x. Right. Now, sine of a sum, sine, cosine, and sine. In the middle, we will have the same sign. The products of different functions, but the sign in the middle are the same. So now, next, of course, we will have the cosine of 2x and then the sine of 2x. Here we can use a double angle. The cosine of 2x, there are of quite a few things that we choose. So which one do we choose for the cosine of 2x? There are 3 of them, right? Cosine square minus sine square, 2 cosine square minus 1, and 1 minus 2 sine square. Right? Which one should we choose? Actually, any of them will work. However, in this problem, we'll see sine, right? So it would be nice if we just use the one that have sine in it. So we're going to go with 1 minus 2 sine square. And then plus cosine. Now the sine of 2x, there's only one option. Two sine, cosine. Now multiply it all out. Give us sine x. Sine times sine square is sine cube. And multiply this together, we have 2 sine and cosine square. Right, so that's good. Now, so we have here this one. How do we go from this to that? One thing we see that in the original problem, we only have sine. Here we have cosine though. So somehow we have to rewrite this in terms of sine. And well, you know exactly what we use, right? Pythagorean identities. So let's do that again. Cosine square plus sine square is 1. So we want cosine square is equal to 1 minus sine square. So that's sine x minus 2 sine cube. And then we have 1 minus sine square. Right, here we can multiply the amount. Two sine x times 1. And multiplying here we have minus 2 sine cube. Right, combine like terms, sine x and 2 sine x, so we have 3. And then the sine cube, we have these 2. Minus 2 is minus 4. And that's exactly what we have. So that's what we have. Simple enough, right? So very straightforward. If we have sine of double angle, then that we only have one. The cosine, there are 3 options. We just pick one to use. Usually it doesn't matter which one you pick, that still work. But sometimes when we choose the sine function, it will go a little more direct to the problem, but any of them should work. Alright, next we have power reducing identities. Right. Proof sine square is equal to that. So how do we prove something like that? So on section 5.1, when we prove it, we can go from one side to the others, or if we can manipulate them, try to simplify and then write everything in reverse, that would be our proof, right? Now let's say if we have this, now we try to get rid of fraction when we simplify them. So cross multiply, so you have 2 sine square equal to 1 minus cosine of 2u. Right? Of course, here we can write cosine of 2u as something that we have earlier. Yeah, cosine of 2u can be any of this. So we can use any of them. However, of course, if we want sine, then we're going to use sine. I'm not going to even, yeah, actually, let's do that first and then we do the other one. Cosine of 2u I'm going to use 1 minus 2 sine square so it's 1 minus 1 minus minus plus. Of course 1 and 1 cancel out and 2 sine square equal to 2 sine square. So that certainly works. If you want to prove it, write everything in reverse. Just write this in reverse, and that is our proof. However, in the note I'm going to write something a little more elegant. Right, first, we'll start with something that we know, double angle of cosine. If we start from that one. Now if we want to solve for 2 sine square, I will move 2 sine square on this side and move the cosine of 2u to the other side, right? So let's say I will add 2 sine square on both sides. And minus cosine of 2u on both sides. When we do that, we will have the 2 sine square will go to this side, and then we have 1 minus cosine of 2u, and then divide by 2 on both sides. Divide by 2. That's what we have. So straightforward. So this, of course, will come from the double angle formula. Except that one a little more difficult to prove, but the first two will be easy. Now if we use this one instead, now if we want to solve for cosine square, what we need to do is plus 1 on both sides. And now we write the 2 cosine square. I just flip the sides. The other side is 1 plus cosine 2u or cosine 2u plus 1. And then divide by 2 on both sides. Right, that's what we have. But the last one I'm going to write on the piece of paper. Right, so that's easy. The tangent square though. Actually, I will start from the right hand side. One minus cosine. I can write that. Which one should we use? I said anything will work, but I will use 2 cosine square. Should use the 1 minus 2 sine square. I'm going to use that simply because 1 minus 1 cancel out, and I just have that. The bottom, I use the 2 cosine square minus 1 simply because that 1 minus 1. So use both of them. The top I use this one, the bottom I use this one for cosine of 2u. Right, 1 cancel out. The top minus a negative turn to positive. And 1 minus 1 cancel out, 2 cosine square. cancel out the 2. We have sine square over cosine square. Of course, that is sine over cosine square, which give us tangent. Right. So, yeah, a little bit different, but we can use that. Yeah, because if we start from this one and we try to solve for tangent square, yeah, that might not be as direct as this formula. Right. So we have an example here, expanding cosine of x of that to the 4th power. Right. So since this is a very long problem, I will start from here. Actually, try to write small. That should be fine. Cosine 4 power of x. Now, the nice thing about this is cosine to the 4th we can write as cosine square and then square. That gives us the 4th power. And then we can choose a lot of different options for cosine square. We can use, actually there's only one option, this one, right? So we substitute that in for cosine square. Right. So in the power reducing identities, the power will reduce, but the angle is going to be double for both of them, for all of them actually. Right. Now for this, we can square the top, square the bottom. Square the bottom, and then square the top. Or better yet, of course that will be 4 at the bottom, right? Yeah, multiply the top later. But for now I will write that. And I will take out the 1/4. So I will write like this, 1/4. And then 1 plus cosine of 2x. Now I will multiply them out. A square meaning multiply by itself. Right. Just multiply it out. 1/4. 1 times 1 plus 1 times cosine 2x. And then cosine 2x times 1. And then cosine square. Combine like terms in the middle. And then we have cosine square. Right. Now, of course, here we're expanding. It did not say where we have to stop. But one thing we know that we still have the cosine square here. So that certainly we can write that as power reducing. And the cosine of 2x here, we can write that as a power, as a double angle. We can use anything, any of those three. But, okay. So if we write that using a double angle, and use power reducing angle for that one. So 1/4, 1 plus 2. Now the double angle look like the answer in terms of cosine though. So I write everything in terms of cosine. So the double angle for cosine to cosine theta to cosine square never mind, we don't want to do that, right? Of course we can do that, but we don't want to do that. The reason we don't want to do that because we're expanding them, and so we're trying to reduce the power too. Like I said, this is not very, it's not clear that how do we want to expand, but in the spirit we want to just keep this with the lowest degree. So we just keep that. Yeah. Now we do need to expand the cosine square. Is the power reducing, so 1 plus cosine of 2 times the angle, right? So every time we use the power reducing, the power will reducing, but the angle is going to be double. Original 2x now is going to double that. Divide by 2. Right. And just like what we have here, I protect the 1/2 in front. To cosine of 2x plus 1/2. Write up 1/2 and then 1 plus cosine of 4x. Right, multiply everything out. 1/4 1 plus 2 cosine of 2x 1 and 1/2. I've just multiplied out 1/2 plus 1/2 cosine of 4x. Right. Combine like terms 1 and 1/2, that's 3/2. And then we have 2 cosine of 2x and then 1/2 cosine of 4x. If we want to, we can multiply it out one more time. We have 3/8 plus 1/2. 2 times 1/4 is 1/2 cosine of 2x. And 1/4 1/2 is 1/8 cosine of 4x. Right, so that is expanding, and we do not have any more power of x. So that is an application for power reducing. Every time we reduce the power, double the angle. Of course, that's one way to do it, and the other way we can also say just stick with that. Right, now half angle identities. Now This will be very easy. What we have is here, if we take the square root on both sides, that's what the plus or minus come from. So I will start with a double angle, power reducing, and I'll go to that. So that should be easy in terms of the proof. First one. Let's start with the sine. So the square, I will not use u, let's use a instead. Power reducing is 1 minus sine cosine of double the angle divided by 2. Now, a could be anything, right? Why don't we choose a to be u over 2? So in that case, we have exactly u over 2. Let a u equal to a over let a equal to u over 2 and substitute into that. So here we have u over 2 and a 2 over u over 2 all over 2. Right, 2 and 2 cancel out. So we have sine square u over 2 equal to 1 minus cosine of 2u. That's exactly what we have here. And divide by 2. Right. Now take the square root on both sides. So we have sine of u over 2 equal to plus or minus 1 minus cosine of 2u over 2. And then of course the plus or minus will be determined, depends on whether we have a positive or a negative on the left hand side. That depends on what quadrant the angle u over 2 is. Right, so that's the first one. That's simple enough. 2. I will do the same thing. If we have cosine square then power reducing is going to be a plus. So sine is a minus, cosine is a plus. The reason I don't want to write u, because later on we're going to use u over 2. So that's why I write a instead. Then same thing. Let a be u over 2. Because we substitute that in here. So sine, cosine p over 2 equal to 1 minus, just substitute in for a, two and 2 cancel out. So we have cosine of u divided by 2. And from here we just take the square root on both sides. So cosine of u over 2 is equal to plus or minus square root of 1 plus cosine of 2u, cosine of u, sorry, over 2. Right. Now, tangent is sine over cosine, so we can have that over that, of course. Now, we'll get back and prove this later. But for now, we just need a little note here. the plus or minus will be determined by the quadrant that the half angle belongs to. Right. Let's look at some example. Find exact values of sine of 15 degrees. So we start with sine of 15 degrees. And of course this is half angle identity, right? So it is a sample right below it. So thinking in context. 15 degrees is half of what? $15, of course, is half of 30. So we can say sine of 30 divided by 2. Yeah, we should write like this instead. 30 over 2. Right. And according to the half angle identity, that will be plus or minus square root of 1. Right. For sine, it's going to minus cosine is of the full angle. So it's not half anymore. It's going to be the full angle of 30 degrees divided by 2. Right, my question is that positive or negative? Well, that's easy. 15 degrees in quadrant 1, therefore it's positive, right? 15 degrees is in quadrant 1. So sine of 15 degrees is positive. Right. And then cosine of 30 degrees. Cosine of 30 degrees is square root of 3 over 2, right? We know it is now positive. Now, cosine of 30 degrees, cosine, so on the left, so square root of 3 over 2. Like that. Now, if we want to simplify this, we can multiply top and bottom by 2, just to get rid of the 2 here at the denominator. So 2 and 2 and 2 cancel out. 2 times 1 is 2, 2 and 2 cancel, we have square root of 3, and then at the bottom 2 times 2 is 4. It is convenient where we split the square root. Square root for the top, square root for the bottom, and that gives us 2 at the bottom. 2 minus square root of 3. Right. A way to check this is let's put this in degree mode, yes, which is that, and sine of 15 degrees. Right. And now we enter this square root alpha y equal to, we have fraction of 2 minus square root of 3. This should be the same. Of course, it's not the same because I entered the wrong one. Okay, once again, this one. The fraction at the bottom is 2 though, so. Yes, these two should be the same, sorry. Right, so that's good then. Next, we have cosine of 22.5 degrees. Same thing. Half angle formula. So what is half of 22.5? No, I should not say that. What I say that 22.5 is half of what angle? Yes, it should be like that. So what angle divided by 2 is 22.5. So to solve for that, we just multiply by 2, and that is 45. Right? So half angle identity plus or minus. For cosine, it's going to be 1 plus cosine of the full angle. Of the whole angle. Divided by 2. And next, 22.5. 22.5 is in quadrant 1. So once again, we choose the plus sign because it's positive. If it's in quadrant 2, then we choose, depends on cosine in quadrant 2 should be negative. Yeah. Cosine 45 degrees. Square root of 2 over 2. To simplify this, we get rid of this 2 by multiplying 2 top and bottom. So multiply that, we have 2 plus 2 and 2 cancel out. We just have the square root of 2 over 4. And just because we have 4 at the bottom, where we split the square root, it conveniently turned it to 2. That's where we split the square root, and so we have square root of 2 plus square root of 2 over 4. Again, if we want to test, and so we type exactly as we see, and it should be the same. Right. Try another one. Now, if sine is that in quadrant 3, find the exact value of sine of theta over 2. So, half angle formula. Half angle, right? Yeah, so this derived from the power reducing. So that will be 2 cosine of theta over 2. Yeah. Now we use theta instead of u. Now, first of all, how do we determine what quadrant it is in? So we can have positive or negative. So first we know theta is in quadrant 3, so let's start with that. Theta. So that means in quadrant 3, so from 180 degrees to 270 degrees, right? That means it is in quadrant 3. Now, let's divide by 2, see what happens. Since we divide by a positive number, the inequality will stay intact, will stay the same. Do not reverse it. So that gives us 90 degrees. Theta over 2. That's 135. Now, if it is between 90 and 135, 90 degrees, of course, is here, and 135 is there. So we're talking about in this part, which is in quadrant 2, right? Because that belongs to quadrant 2. So this is in quadrant 2. So in quadrant 2, sine is positive. Right, so that's how we get it's going to be positive. If cosine is going to be negative. Right, so the rest is simple, right? Just put in the number 1, and it's not as simple because this one is sine, and we have cosine. Ouch. Right. Now, one way to do that is using the identity, Pythagorean identity. So we have I should see that from the beginning, so I start to write smaller. But remember, we can always have that. So this we want to solve for cosine. Is equal to 1 minus sine square, right? 1 minus sine square, and sine square is that. So what is 1 minus negative 5 over 13 square? So let's get a fraction. Right. So that equal to 144 over 169. Taking square root on both sides. Of course, that's going to be 12 over 13. But is that positive or negative? Notice that this is in quadrant 3. So cosine of theta is negative. Right. So, yeah. Or of course we can use x, y, and r to solve for cosine. I don't have a lot of space, so I just have to use this one. Because in quadrant 3, cosine is negative. So that certainly works. Right. So what we substitute there is negative 12 over 13, not that one. Right. And to simplify this, negative, negative, that's plus. Thirteen cancel, we have 12. And over 2 times 13, 26. So we have square root of 25 on the top and 26 at the bottom. Of course, if we split, it's going to be 5 over square root of 26. And usually we multiply square root of 26 top and bottom to get the rationalize the denominator, but I don't have to. Yeah, we just have to do this if we want to. In that case, give us 5 over square root of 26 over 26. Of course, in that case, we don't have the square root at the denominator, but that's what we have. So be careful. In the power reducing or half angle or double angle, it's going to be cosine. I mean, not double angle. Double angle we can use different, but it's going to be cosine. So in this case, the problem only gives us sine, so we have to find sine first. I mean, find cosine first, which is negative 12 over 13, before we do the math, and that's what we have. Right. Next, I'll verify this identity, so we don't know if this is true or not. But the easiest way to prove, because when we have the half angle formula, that could be positive, could be negative, so it'll be more difficult to prove. So the easier one to do is just like what we did before. Let x over 2 be something. If we let that equal to u, so x is equal to u, and the identity becomes the equation becomes, we don't know if this is an identity or not. X is going to be 2u. Cosine x over 2 is going to be u. And sine of u 1 plus cosine of 2u. Right. So that is a lot better to write like this. Right. Now, after which one is similar to prove, I probably would just go from this side to the other side. So we start from the right hand side, because this looks a little more complicated. So we start with the more complicated side and try to simplify it. Now, cosine of 2u, double angle for u, 2 times u. So what identity we can use though? Remember, there are 3 options for that. 1, 2, 3. So now here we have 1 here. Of course, any of them will work, but I prefer to use the one that is more convenient, and the more convenient is this one. The reason I use this, because this one has the -1 with the +1 there. That turned out to be more convenient, right? So cosine of 2u is 1. Right, use this one in the middle. Two cosine square -1. Right. Yeah, that's one. Because the +1 -1 conveniently cancel out, so we have sine of u. Let's just write out. We have plenty of space. And 1 and 1 cancel out. Now, the cosine square is that multiplied by itself. Cosine of u times cosine of u. And finally, this is a double angle of sine of 2u, right? That gives us sine of 2u, and then cosine of u. And that is equal to the left hand side. So, here's proof. Talking about plenty space, we did say that we'll come back and prove the tangent identities. So tangent of u over 2. Of course, if we let sine over cosine, then we have the first one. That's easy. Now let's try to prove equal to. Let's do the first one then. Okay. So prove tangent of u over 2 equal to. Yeah, let's just pick one of them. The other is the similar. Right, let's prove that. So, similar to here, if we don't want to work with the half angle, because the half angle usually involves the plus or minus. So let's square both sides. Sorry, not square both sides. Let's do the substitution. Let u over 2 be the angle. Let's say A. So in that case, u is equal to 2a. Now we substitute into the identity. So the identity becomes tangent of. So if we let that be the case, then tangent of u over 2 is tangent of a equal to sine of u. U is 2a. And 1 plus cosine u is 2a. Right. Obviously, we start from the right hand side because that's a little more complicated. Now sine of 2a. Now we have the double angle for cosine. So which one do we use? So very similar to the previous example, previous problem. If we write this as 2 cosine squared minus 1, the plus 1 minus 1 will cancel out. So that conveniently cancel out. As mentioned before, any of them will work just fine. Right, so 1 minus 1 cancel out. And then the sine of a double of the angle. We only have one option for that. It is 2 sine cosine. And of course the angle should be A. So on the top we have 2 sine A cosine A. The bottom we have 2 cosine square. We can cancel the 2. The cosine square cancel with the cosine on the top. So we have a sine over cosine. Which is tangent. And because that's what we need to prove. Right. So we start with the half angle formula. Will be more difficult. So in that case, make a substitution. So then we do with double angle, and we don't have to worry about plus or minus sign. So that is the proof for that identities. Of course, we can use the other one and prove to be similar. Right. So, but with that, this is application of double angle, half angle, power reducing. Of course, all of them will come from these identities. Right. I will stop this section here. Thank you for watching. See you in another video in trigonometry.